Hello, calculus fans. Let's talk about moments of inertia. So the moment of inertia, which is also called the second moment, of an object of mass m about an axis, is defined to be mr squared. R is the distance from the particle to the axis. We can extend this concept to a lamina with some mass density function, and which occupies a region D, and we can do it just like we did for ordinary moments. If we do, we're going to get some formulas for the moment of inertia of the lamina about the x-axis. All right, we're not going to go through the calculation involving the limit of Riemann sums. I'm just going to give you the integral formula. So the notation we'll use for the moment of inertia about the x-axis is I sub x. And that's going to be equal to the double integral over the region of y squared times the density. So this is different than when we did just the ordinary moment about the x-axis. There we didn't have a y squared, we just had a y. And in a similar way, we can compute the moment of inertia of the lamina about the y-axis. That's going to be I sub y, and that's the double integral of x squared times rho. It is also of interest to consider the moment of inertia about the origin. The other phrase that you'll hear to describe that is the polar moment of inertia. We're going to use this to describe rotational moments. So we'll write I sub 0, and it's the double integral over d of x squared plus y squared times rho. The way the physics works is that the moment of inertia plays a very similar role in rotational motion that mass plays in linear motion. The moment of inertia of a wheel is what makes it difficult to start or stop the rotation of the wheel, just as the mass of an object is what makes it difficult to start or stop the linear motion of an object. The larger the moment of inertia of a wheel, the harder it is to start or stop the rotational motion. The larger the mass of an object, the harder it is to start or stop the linear motion. So as an example, let's find the moment of inertia about the center of a homogeneous disk. The word homogeneous means that the mass density is constant. So let's say rho of xy is equal to k for some constant k. Let's say that the boundary of the disk is the circle x squared plus y squared equals a squared. So in polar coordinates, as usual, we'll describe the region by saying that r goes between 0 and a, and theta goes between 0 and 2 pi. So here's how we'll compute the moment of inertia. So I sub 0 is equal to the double integral of x squared y squared times k. Remember that k is just the mass density function. So we put everything in to get k times the integral from 0 to 2 pi times the integral from 0 to a of r squared r dr d theta. The r squared comes from x squared plus y squared. The r, well, that's just the r that you're supposed to have when you do polar coordinates. Split everything up. We get nice looking integrals, very easy. And the final result here will be 1/2 pi times k times a to the 4th. Now I don't want to leave it like this because I don't want to have something where the proportionality constant is going to sit in there, so we're going to make some changes. Notice that the mass of the disk is just density times area. That's because it's a homogeneous disk. We can rewrite the moment of inertia of the disk about the origin, like so. We can say that I naught is equal to 1/2 pi k a to the 4th, and then just pull together k pi a squared and replace that with m. So instead of having that proportionality constant, what we have is the mass. And that's the general way that we want to be able to write down the moment of inertia of an object. We want to have it as a function of its dimensions and its mass. not some proportionality constant. Okay, that's all for now.